Hello everyone, and welcome to the first Eng 130 video tutorial. My name is Clayton, and I will be your guide through the series. In this example, we're going to cover the addition of two vectors using the parallelogram method. Alright, so moving on to the example. From the picture, we see that we have two forces. The first one is going to be 800 pounds, and the second one, 500 pounds. And the question asks us to determine the magnitude of the resultant force and its direction measured counterclockwise from the positive x-axis. And that last piece of information is really important, and we'll touch on that in a bit later. For simplicity in this tutorial, I am going to label each of the initial vectors with a color, just to kind of help you show where I'm getting the numbers from, and it's easier just to kind of reference. So the 800-pound vector is going to be a blue vector. If I can go back, it's going to be a blue vector, and it'll always be blue through the remainder of this example. And then the second vector, the 500-pound vector, it's going to be a red vector. So I'll just make that real quick. Perfect. So we have two vectors. The first one's 800 pounds. The second one's 500 pounds. And the first part of the question asks us to determine the magnitude of the resultant force. And basically that's just asking for the size of the two forces when they're added together. So it's quite simple. Quick note before I start the example is some of you might be a little scared of pounds. Yes, pound is American. We will, it's not Canadian. You will rarely see it in your classes, but you will sometimes. I just think it's good to know. I didn't really have much experience with the American system until later on, but it's definitely handy to know. All I'm going to say to you guys, and this is all you'll have to need to know, is that a pound is basically like saying a newton. A lot of people may get confused and think that pounds is the same as mass, like kilogram, but it's actually not. It's a unit of force. So whenever you see pound anywhere, just think of it as a newton. It's very simple, and you will use this for the rest of your life, so it's kind of a win-win. All right, so moving on to the parallelogram method. There's two key steps you have to do to start this method, and it's actually really simple. So the first thing that I like to do is I like to draw just a little axis down on the left hand side. So I just go down and I go across, and then I like to say that this is my starting point. So from here, what I do is I take the first vector, and this is kind of a little bit of a trick. The first vector can be the 500 pound or the 800 pound. It does not matter which one you start with. But for the sake of this example, I'm going to start with the 800 pound vector. And what I do is I take the butt of the vector, so the point at which it starts at, the point I'm kind of circling right there, and I place that at my origin, right there, down there. And then I simply just place that vector onto the origin. So it comes up, comes across, and that's the 800 pound vector. And just to make sure that we're all on the same page, I'm just going to also label it as 800 pounds. And labeling things will make things a lot easier moving forward, especially when it gets more complicated. So the second step to the parallelogram method is also actually really simple. What you want to do is you want to place the second vector onto your drawing space. So for the 500 pound vector, what we're going to do is we're going to start at the butt again. So I'm just going to circle it more in red, just like I did the first one. But here's the trick. Instead of placing the butt of that vector at the origin, like I did with the 800 pound vector, I'm going to place the butt at the tip of the 800 pound vector, like so. And then what I do after that is I can simply just draw my vector. So, oh, that didn't work out too well. And then I'm going to tell you guys another quick trick after. Perfect. So that'll do fine. We have another vector, and again, it's always nice to label 500 pounds, so we know the size of that. So that's basically it. That's the hardest part of this example, is just remembering those two steps, because after that it's all just trigonometry. And I say that lightly because I know trigonometry can really suck sometimes, but there's also tricks for that in this course too, and I'll be sure to tell you all of them. So with the two vectors placed, we can actually now draw the resultant force of the two vectors. And what that's going to be is I start at the origin, so now it's green, and you can kind of see it. And what I do is I go from the origin to where the second vector ended. And I'm just going to erase that. Still getting used to this a little bit. To where the second vector, perfect. So this green vector right here, that's actually going to be my resultant force. So I just like to label it as F sub R, my resultant force. And determining the magnitude of that force is actually the first part of this example. So let's move on to how do we solve that. Well, if you look at this, we have a triangle. And this triangle abides by all the trigonomic identities that you've learned in high school, even middle school. So we're going to try and apply those into this triangle to try and solve for some of the unknowns. But here's the little bit of the trick, is this triangle is not a right triangle. So very, 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 very seldom will you ever have the c squared equals a squared plus b squared. We'll use a modified version of that, as you'll see later, but it can sometimes not be that simple. But before we get into that, what I also like to do is kind of the final step is just take any angles I know and also put them into the space. So looking at the top here, I'm just going to highlight it. We know that the blue vector makes a 40-degree angle with the horizontal axis. So if I come up here, I can draw this angle, and I know that this angle right here is going to be 40 degrees. So that's nice to have. And then the second angle we know is that the red vector makes a 35-degree angle with the horizontal axis. So if I were to draw a horizontal axis at the top here, I know that this angle here, that angle is going to be 35 degrees. So that's nice to have in there as well. So from here we can begin solving for everything. So before we do, I'm going to show you what we'll always be using for the parallelogram method, and then which steps which steps you should take based on that. So before we get into that, let's just draw a random triangle. So it goes up, comes, oh, I didn't know I can drag it. Perfect. Comes across, and then it comes down. So this triangle, let's say it has lengths A, B, and C, and then it has interior angles, capital B, so that it's because it's across from the small b, across from the small c, so we'll call this interior angle capital C, and then finally this interior angle A. So if you have a triangle with this geometry, there's two laws that we can actually apply to the triangle. So the first one is called sine law, and I'm sure you guys have heard this in class, and I like sine law. It's very useful. You'll definitely use it in later years for geometric purposes, but I like it because it's short and sweet, nice and simple. So what sine law states is that A over the sine of interior angle A is going to be equal to B over the sine of interior angle B, which is equal to C over the sine of interior angle C. So I'm just going to erase this real quick, make it look a little bit neater. But that's it. Nice and short and sweet. So with this law, if you were to know two lengths, let's say, let's go to red. Let's say that we know A and we know B, as well as we know the interior angle of one of those lengths, let's say sine A, because we know A, capital A, we can actually solve for interior angle B. Or, let's just say that instead of knowing B, we somehow knew C. Well, then we can solve for interior angle C by saying that A over the sine of capital A is equal to C over the capital of sine C. So that's a very nice law to have. The problem that I have, or not that I have with sine law, but the problem that you guys will more have with sine law is that it's usually never the first step. It's easy, it's more simple than the second law, but it's usually never the first step. And the reason why is because very rarely will we start with an interior angle. We'll usually have the two magnitudes, let's say A and B, but very rarely will we have that capital A or capital B. That's why we usually start off with the second law. So I'm just going to write here, number 2, and the opposite of sine, cosine. So cosine law. Oops, I always click. All right, cosine law. And what this law states is that c squared is equal to a squared plus b squared. Easy, right? Well, actually, that's not quite it. There's a little bit of a factor, so it's minus 2ab times the cosine, hence cosine law, of the interior angle C. And that's really nice because if we know the magnitude of the three vectors, or an interior angle, sorry, the magnitude of two vectors and an interior angle, we can solve for the magnitude of the third vector, which is almost usually the case in these examples. When we ask you to find the resultant force, we use the two first vectors, A and B, as well as an interior angle, to try and solve for the resultant force, which would be in this case C. However, this can be modified, and it's very easily modified, which I'll show you here. This is just one of the cases. You can also say that A squared is equal to B squared plus C squared minus 2 BC times cosine of A. So it's really easy to see how it's modified. It's always going to be those two magnitudes, but whatever you're solving for, so in this case I'm solving for A, the interior angle we're going to use is going to be A. So then likewise, you can also just do one more rearrange to find that B squared is equal to A squared plus C squared minus 2AC times the cosine of B. So if you guys don't want to remember these formulas, even though they're pretty easy, I think that a lot of you guys can memorize them, but don't worry. You don't have to, because they'll be provided on your formula sheet. So don't be too worried about this. It'll be provided for you. All right. So looking at these two triangles and just comparing our triangle that we drew down here. Oops. Our triangle that we drew down here, and if we compare it to our actual situation, well, looking at it, which color should I use? Let's use pink. We know A. A is the 800 pounds. We know B. B is the 500 pounds. And what we're looking for is C. So if we look at this, we don't know interior angles A, B, or C. So it's probably not the best to start with sine law. However, if we go down to this formula right here, we have a nice formula for C. It requires A, which we have, B, which we also have, but then the last thing it requires is that interior angle C. So if we go up to this triangle, interior angle C is that angle, so going up to our situation, we're going to have to find this angle right here. And this is usually the case. You'll always have to start with finding interior angle C. As you guys will see, this is going to be the hardest part of the parallelogram method, but once you guys get this next part, you guys are fine. You guys will be ready for the labs and the questions. All right, so what I like to do to try and find this angle is I like to take what I call a little snapshot of kind of this point here. So if I go down here, I'm going to draw another horizontal axis. Perfect. I'm going to draw a vertical axis. And then what I'm going to do is I'm going to draw the vectors that I have coming in. So I know right from the beginning that I have a blue vector of 800 pounds, and that's coming in. So all I do here is I'm just going to draw, oops, just erase that, make it a little bit nicer. Perfect. I got 800 pounds coming in, so this is my 800 pound vector. I'm not going to label it because the purpose of this isn't the magnitudes, it's more geometry. And I also know at this point I have another vector coming out, which is the 500 pounds. So I'm just put this down, and again, what we're looking for is that interior angle between these vectors. So what we want here is this pink angle, which is C. So the next part, what I like to do is just figure out, all right, well, what angles do I already know? Well, if we look up here, we know that the 500 pound vector makes a 35 degree angle with the horizontal axis. So if I come down here and I zoom into this one, I already know that this angle here is going to be 35 degrees. So that's really nice. So theoretically, I can solve what that interior angle C is if I know what this angle is right here. The problem is I don't quite know that angle. But what we do know is that this blue vector makes, let's draw an axis. We already know that this angle here is 40 degrees. We know it makes a 40 degree angle with the vertical axis. So there's two things that we can do here. And I'll show you kind of what I like to do because it always works. Or I can show you more of a proof if you're not so sure about the quick tricks and want some actual proof. We can go that route. So what I like to do, which is the proof, and this will always be true, so always I like to do this, is if this angle is 40 degrees, this angle is 40 degrees. And it's just kind of a quick trick. It'll help you solve things really quick. And if you're wondering why that is, and again, I would remember this, it works all the time. It's because if I were to make a little right triangle right here, we know that that's going to be 90 degrees, as well as the sum of the triangle is going to be 180 degrees. So just by this little triangle, we know that this angle here is going to be 50 degrees. And then if we look at this right triangle here, we know that this is going to be 40 degrees because it's going to be 90 minus 50. But in the end, now we have our angles and we can simply solve and say that our interior angle, which is again C, it's going to be equal to 180 degrees. So I'm going to take the whole angle between that horizontal axis minus the 35 degrees, subtracting this part right here, and then minus the 50 degrees. So then I'm subtracting this part over here. And what we'll end up getting is C is equal to 95 degrees. So that's perfect. Now we have our interior angle. We can substitute it into cosine law to find out what exactly our resultant force is, Fr. So remember, I'll just write it down so in case you guys forget what I'm doing the cosine law. And from that, we know that A is going to be 800. We know that B is going to be 500. And we know that the capital C, which is the interior angle, is going to be 95 degrees. So now I'm going to write out the equation. A lot of professors just say, well, those are the parameters, sub it in. Sometimes it's not so clear. For example, the angle. Should it be entered in radians or degrees? The answer is degrees, but some of you might get a little mixed up on that, which I'll remind you again before midterms. Make sure you have your calculators in the right form. So many people go into radian mode for especially math class and forget to switch it back. But substituting everything in, we get C squared, which is C squared is what we're solving for, but what C squared is in this is actually FR, so resultant force squared, and that's going to be equal to 800 squared plus the 500 squared minus, and then don't forget the 2. A lot of people forget the 2. It throws things off completely. Minus 2 times the 800 times the 500, and then followed off with times cosine of 95. So again, input 95, keep it in degrees. And what happens is when you put this exactly into your calculator, you'll get that FR, well, after you square it too to get rid of the squared on the FR, you'll get FR is equal to 980 pounds. And that there is the magnitude of the resultant force. So I'm just going to underline it so I don't forget. And that's the magnitude of the resultant force. So if we look at the original question, this first asked, determine the magnitude of the resultant force. Well, we can put a check. We've done that. So the question's halfway done. And again, you've seen all the hard tricks. Once you get to this spot, it's pretty easy. So the second one asks for its direction. So we know the length of the vector is 980 pounds, but we don't know how it's orientated. So what we want is its direction measured counterclockwise from the positive x-axis. So if we look at this figure, this right here is our x-axis. So we'll just take it out to the end. Perfect. So what it wants is actually, and I'll actually draw this in a different color. Let's go purple this time. Why not? What it wants is this angle here. And I already used theta. Did I use theta before? Oh, I used C. All right, perfect. So we're going to call this angle theta. And this is very important because this question is nice. It asks you measured counterclockwise from the positive x-axis, which you guys may or may not know that in engineering this is the standard. So if we ask you for a resultant force, the magnitude and direction, chances are we won't say measured counterclockwise from the positive x-axis. We're just going to tell you we want its direction. So the standard you guys should always go to is measured counterclockwise from the positive x-axis. So you always want this angle. Now, actually, let's just kind of draw onto the side here. Let's say that these are my axis, and the vector was going down like that. What angle you want is, again, from the x-axis, so you always go to the positive x, which is going to be on this side, and the angle that we want is going to be like that. So it's going to be somewhere between 180 degrees and 270 degrees. So keep that in mind. And then let's say that this angle here is 200 degrees. What we do for its direction is we state that it's 200 degrees. And then what we should do is we just make a little angle sign and then an arrow showing it's measured from the positive x-axis. And that right there is the correct format. If you were to go here and say that this is south of west or west of south, that's incorrect. We don't do that here in engineering. So that high school physics, it'll get some of you because you have no idea how many students in the first lab use those directions as their answer, but it's completely incorrect. All right, so what I like to do is similar to up here. Up here we wanted to find C, so I took a little snapshot of that corner. Well, what I want to do here is I'm going to take a snapshot of this corner and try and find that theta. So first thing I like to do, again, is just draw some axes, make it nice and clear, because the key to engineering, and this applies to a lot of things, not just first year, this will apply all the way to fourth year, especially if you take civil, and you guys will see especially later in the courses, a lot of the problems can be easily solved as long as you have really good drawings. Not really good as in very artistic, but just clearly labeled showing what parts are where. So in this case, if we go up here, we know we have the 800-pound vector kind of going out like this. We look back, we have a green resultant vector, which comes out to the side. Perfect. So again, I'm not really labeling the magnitudes of these vectors because I'm just looking for angles. I'm looking for geometry, so it doesn't matter too much. So if I go up here, what angles do we know? Well, we know that that right there is 40 degrees. So this angle, oh, I went out. Perfect. Oh, come on, there you go. 40 degrees. Perfect. So that's 40 degrees. We know that we have a purple angle? Yeah, purple angle here. That's theta, and that's what we want. That's our final answer. So we can just tell by intuition that we'll be able to solve this problem if we know the remaining angle here. And if we look at this triangle down here and compare it to the one up top, we can tell that that is actually interior angle B. So what I'm going to do is just label this as B. And now it should be obvious what we're going to do. We're going to solve for interior angle B. So let's look at our formulas real quick. So there's two that have interior angle B. And I'm going to go back to the pink just because it really shows well. Actually, I'm going to go to the purple because we're dealing with that angle. So there's two formulas. One is there is a cosine formula that has interior angle B there. B squared is equal to A squared plus C squared minus 2AC, blah, 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 blah. And actually, we know everything in this formula. We know B, A, and C. We can rearrange it, and we can get interior angle B. So that's a viable option. I don't recommend it though. And here's why. Is a lot of the mistakes that all happen in first year, and I know that you guys don't think this is going to be you, but it always is at some point. And I was one of those guys. Calculator mistake. That won't happen to me, but it's happened to me on midterms more than once. What I recommend is avoid this formula if we're solving for an interior angle. And the reason why is just there's so many terms that the algebra to mix it around it's pretty easy, but there's just a greater chance of you making a mistake. So I like to go to sine law, and that's why I was kind of hinting at earlier. It's shorter, it's sweeter, which is why I prefer it. So if we look at this one, we're looking for, I always switch to eraser. We're looking for that interior angle B. We already know little case b, same with a and c. So that's not a problem. So we can go either side at this point. We can go to the left side, but we're going to have to solve for interior angle a first, all the way to the other side. And although we can do that, why take extra work? And that's another thing. I'm a big fan of just, get to the answer. We don't need to show all this fluff work if we don't have to. If we look at the right side, we need interior angle C, but we already have that. Oh, so that's perfect. So if I were to create a box around this equation here, and if we look at this box, we know everything in that equation except for one term, which is going to be interior angle B. So if we go down here, we can actually write that equation out while subbing in terms. So just to recap, right now I'm using sine law. And if we look at what it says, we want B over the sine of interior angle B. So if we look at these triangles, B is the 500-pound force. So that's another trick. A lot of you will put the 800-pound force. So if we got 500 divided by the sine of B is going to be equal to, and if we look up, it's going to be C divided by the sine of interior angle C. And C we solved for is 980. So right here, we're just going to go 980 divided by the sine of interior angle C, which we know is 95. And what you'll get is that B is equal to 30.54 degrees. So this leads me to kind of my next point with you guys, and that is just final answers. So this interior angle B is not our final answer. And so we have to think, well, if we keep the B as 30.54 all the decimal places, we're going to get an answer. However, if we were to cut B down to, let's say, 30.5 and use that in the remaining calculations, we'll get a slightly different final answer. So now you guys have to ask yourselves, which one do I use? Should I try and keep the decimal spaces? Should I cut it down? Well, the answer is it's up to you. Us as markers and us as professors, we know that there's going to be the variations within the final answers, so don't worry about it too much. And what's going to happen is in the labs, you can use whatever calculator you want. So, of course, people are going to be using the very nice fancy calculators that can store 1 million variables. So in the labs, you might choose to save all the variables. But as you guys will soon learn and soon hate, in the midterms, you're given these crappy little, well, not given, you guys have to get them yourselves. Please make sure you have one and know how to use it. But there's crappy little sticker calculators that can barely save, I think, maybe 4 or 5 variables. So keeping all those decimal places isn't such a good idea. So again, it doesn't matter. If you want to save them, go ahead. If you don't want to save them, it's going to be completely fine. You can just keep it as 30.5, and we know that there's going to be variations in the final answer, so it'll be fine in the end. All right, so moving on, the last part of the example, we know that our theta here is going to be equal to 90 degrees minus the 40 degrees. And then, of course, minus b, which is the 30.54 ... degrees. And what we'll get is our theta is equal to 19.5 degrees. So that's another quick thing I should probably mention is in my final answers, like let's say the resultant force up here, I just have it as three significant digits. It's a good point to tell you guys, though. In this class, always use three significant digits. It's not like high school where they try and trick you with the sig digs, with the addition and the multiplication. So sometimes it's 4, sometimes it's 3. What I like to say is always keep it 3. You guys won't get marks deducted as long as the answer looks nice. If you have an answer that's in the thousands, I'd keep 4 significant digits and not do the 1.9 times 10 to the, like that to me just looks so ugly. So I always just try and make it look nice, and usually the case it's going to be 3 significant digits. So that's just another thing. All right, so we solved both parts of the question now. We have the magnitude and we have the direction. But the problem is we're not done, because this is engineering now. This is the big leagues. So one final thing that you guys should definitely do is you guys have to state your final answer. So at the bottom here, I go FR, so the resultant force is equal to 980 pounds. And then I also have to state the direction. So 980 pounds, and we know it's 19.5 degrees measured counterclockwise from the positive x-axis. So that's the final answer. Now we can say that the problem is finished. And then another thing I like to do, and this is very important because some of you guys truly amaze me. I've gotten labs that take me 3 or 4 pages to solve, and you guys solve them on half a piece of paper, showing more work than I have, of course, too. And the writing's so small that it's hard to see your final answer. So what you should do, and this is highly recommended if you don't want to get accidental marks off, box your answer. So just create a nice box around it to tell the marker. No, I was hoping it would correct my box, but I'm going to try again to hopefully get it. So just create a box around the final answer. Oh, well, that didn't work, but I think I can just... Oh, perfect. And now that's the final answer. Because another thing, too, is let's say that you're going super fast. And this is going to be the midterm. I'm kind of foreshadowing the midterm because this will be that'll be your guys' first real taste of university. And well, trust me, it doesn't taste very good. But what happens is you get an answer, you move on to the next question, and then later on you're thinking, oh, crap, that answer is incorrect. And instead of trying to erase everything, because it just becomes a mess, just cross it off, put a new answer in, and box your final answer. It's okay if you have an answer before. We will only take the boxed answer. So just kind of another thing to keep in mind for later on. All right, so this question's done. If you guys show this work, you guys will get full marks. But I'm going to show you guys something else, and this is for the non-believers out there. So if we go back to the beginning of the question, I said something at the very first step. I said what we want to do is we want to take a vector and place it onto a drawing space. And what I did is I took the 800 pounds, I threw it on there, and then moved on to step 2. But in there really faintly I said it doesn't matter which vector you start with. And this is true. And I know a lot of people are going, oh, well, you know, he's doing the videos. He's probably knows what he's talking about. But then, of course, and trust me, I know you guys are out there, and I'll see you guys in the semester. It's the people that tell me, I don't believe you. You're full of crap. And for you guys, I'm going to show you this fact, and hopefully you'll believe me after that. So I'm going to do the problem, but I'm not going to show as much detail. I'm going to go rather quickly. But I'm going to show you that it doesn't matter which vector. So let's go down here. Remember what I like to say. The first step I like to do is create my axis at an origin point. So I'm going to start at the top this time. Go down. So this is going to be my starting point right here. And what I said is I'm going to start with the 500-pound vector. So what I'm going to do is I'm going to go here to here. 500 pounds. So this is my first vector. 500 pounds. Again, for simplicity, got paper everywhere. I'm going to label it 500, looking real good. Perfect. And now the second part is I take the second vector, which is the blue one, the 800 pounds, and I put it at the head of the first vector and draw it out. So it kind of goes up like this. So this right here, that's the 800 pounds. So I'm just going to label it 800 pounds. So here's kind of a little bit of a trick. Well, actually, I'll show you guys after. But the final step is I go from the origin, which is all the way over here, and I make a final vector, which is the resultant vector, the FR. And you guys can already kind of see it's going to be the same, because look at how FR is positioned there and positioned here. They roughly look the same. But that comes with the drawing. So that's another thing. I'm going to kind of, maybe I'll do this in orange just so you guys can see. Notice the length of the 500-pound vector and the 800-pound vector. Remember, the 500 pounds is magnitude. It should be the length of the vector. So since 500, of course, is smaller than 800, I drew it shorter. Now, the math of cosine law and sine law, you don't need to draw your diagram perfect. It doesn't matter. I can draw the 500, if I wanted to, I can draw the 500 like this, and then the 800 like this. The math will all work the same, but this is where it's going to confuse students, is if I'm connecting the resultant vector, oh, I pressed the eraser. Hold on. Oh God, did I ever? Oh wait, I got a back button. Perfect. So if I'm drawing the resultant vector now, and I go from the origin all the way out here, a lot of people are going to say, well, that angle now that it makes with the axis is actually going to be 300 and some degrees, when it's not. The math will tell you it's not, and of course it isn't. But what's going to happen is you guys will still get the same angle, 19.5, and then a lot of you are going to go, huh, well, maybe it's 19.5 clockwise, and then you guys put 19.5 here. Or some of you will take the 360 and subtract it. That's not the case. So the one nice thing about having a nice drawing is it'll kind of help you with trigonometry later, which is, you're going to need to know that. All right, so I'm just going to label a couple things into this just to kind of smooth the process. As I said, I'm going to go a little bit faster. So we're going to need this interior angle here again, which is going to be interior angle C. I like to say it's C because it's in the cosine law. That's what we say it is. It's C. I'm going to draw a horizontal axis here because I'm going to put in some angles because I already know that this angle right here. Oh, I keep switching to eraser. This angle is 40 degrees. I know that this angle is 35 degrees. And then also going to go back to that purple / magenta, and this is going to be the theta, which we're going to need to find in the end. But if you guys look at the diagrams, the forest looks the same, theta looks the same. We just come at it from a different angle, really. And this will change a couple things. For instance, do you guys think the interior angle C will be the same? I'm just going to let you guys think about it. Or do you guys think that all the parameters will be the same? Just think about it, but you guys will see in the end. All right, so going on, we need interior angle C. And that's where, oh, sorry, I forgot to get out of magenta mode. Go back to black. Here we go. Perfect. So in order to find C, I need to find this part right here. And in order to find that, well, what I can do is I can find this part here. So this goes back to the trick I said. If that's 35 degrees, then this angle here is 35 degrees. So what we can say is that C is going to be equal to, and then what I'm going to do is I'm going to go 40 degrees plus, and then I'm going to add that little star part. And we know that that star is just going to be 90 minus 35. And what you'll get is C is equal to 95 degrees. Now, this isn't a coincidence, and this is kind of something that you guys should kind of keep in mind. 95 degrees. Up here, 95 degrees. Those angles are the same. So that's nice to know. Those angles are the same. So maybe kind of keep that back in your mind for future problems. However, you can't say that everything is the same. I told you I'd show you, but I'm just going to kind of get a spoiler alert because half you're going to go, oh, it's all the same. Click, close on the video. I'll see you guys later. But then in the lab, it's going to kind of bite you in the ass. So this is 95 degrees. We'll move on. We can solve FR. Well, if we look at FR and the cosine formula, it's actually just going to be the exact same, except A and B are swapped. But in the math, it doesn't make a difference. But I'll put it anyways, just so you guys know. So FR squared. Keep in mind the squared, guys. You guys will forget that. I can see it now. going to be 500 squared plus 800 squared minus 2. That 2 is also something people like to forget. And I say people, I'm really meaning me, because I've forgot it so many times. And then times cosine of the interior angle C, which is the 95. And again, it's basically the same stuff, just rearranged a little bit different. You'll get FR is equal to 980 pounds. And, oh, I guess I should have said this earlier. It's important to put units. Don't forget units, guys. It's pounds. All right, so now this is where it kind of differs a little bit. And that's finding that angle, that magenta angle theta, the direction. So what I like to do, I know I'm going to be dealing with kind of that little area, so I'm going to kind of expand it to hopefully show me what I should be looking for. So I make some axis, go to here. I know I have two vectors coming out. I got that one, and then I also have the 500-pound red vector. Doesn't really matter which way, how picky you are with the angles. What's kind of nice is we already know that this is 35 degrees. So it's a little bit quicker. And we know that what we want is this magenta angle here, this theta. So looking at this, if we were to know that total angle, so if we were to know this total angle, oh, oops, go back, oh, no, I'm back too far, hold on, alrighty, theta, now we go back to this. If we were to know this total angle, then we can easily find theta. So looking at here, well, that total angle there, that's actually interior angle, so all the way up, that's interior angle B. So what we can do is we can use the sine law yet again to find that angle. So just looking at this, we can go sine law now to find the total angle. So what we're going to have is we're going to have B over the sine of B. So I'm just going to go over sine of B is equal to C, which is 980, all over the sine of the 95. And the reason why I didn't put B in yet is because let's just take a look at the picture here. B is on the far side, okay? So if we look over at our diagram here, our B is the far side. It's going to be the 800. Now, a lot of you guys will just put the 500 in because it's shown in this picture right here, but that's incorrect. So I just wanted to give you guys a heads up. Make sure you guys are always looking at this triangle. And I think that this triangle is actually also provided on the formula sheet. So I may be wrong, but I think it is, which will help you guys. So make sure you guys are kind of keeping track of that. So if we go down to here, we put 800 in. And then what we find is that that interior angle B is going to be 54.4, oops, 0.41 ... degrees. So I keep all the decimal places. It doesn't matter too much. So then what we can do is we know that, oh, I'll switch to magenta to show you guys what I'm doing. So our theta is going to be the 54.41 degrees. So that's the total angle there, minus the 35 degrees. So what we get is our theta is going to be 19.5 degrees again. And that's our final answer. But again, even though we have all this stuff, what we should do is go FR, just state the final answer. We know it's 980 pounds. And we know it's 19.5 degrees measured counterclockwise from the positive x-axis. And I draw a crappy box, but luckily for me, oh, I was gonna say I get to correct it, but I don't get it corrected and make a fool out of myself. We go back around, come up. All right, I'll get this last try. This is the end of the example, so if you guys want to watch me struggle, you guys can watch me struggle. Perfect. Well, kind of, but it works. All right, perfect. So this concludes the first example. In the next example, we're going to add 3 vectors. So the methodology is very simple to this, very simple, similar to this. If you guys know what you're doing here, you guys will be fine. However, there's one kind of little trick to it, and so it's definitely worth watching. All right, so that is the end. Thank you guys so much, and I will see you guys in the next video.